Assalamu alaikum and good day everyone. In this video I'm going to discuss example A4. So for those who haven't watched the videos provided in Google Classroom, please do so or click on the link provided. Okay, for this example we have this block diagram here. We have a system 1 over s, s plus 1, s plus 2, and we have a gain k, and we have a unity feedback here. From this, we can find the characteristic equation. The characteristic equation is given by 1 plus GH equals to 0. So basically, where does the characteristic comes from? Is basically from the closed loop transfer function. We have in here is actually G1 plus 1 plus over GH. So this GH equals to 0, it becomes a characteristic equation. And we replace G and we replace H into the equation. What we have is actually we have this characteristic equation, this polynomial s power of 3, 3s squared plus 2s plus k equals to 0. And then we can find the value of k, the range of k, by we replace the polynomial into the Routh table. So we have this polynomial here, the coefficient of polynomial is 1, 3, 2, k. So we replace it into, we insert it into the Routh table, so we have 1, 3, 2, k. Alright, so to find this value, basically what we do is we multiply 3, 2 equals to 6 minus 1k equals to k, and we divide by 3. So we get 6 minus k over 3. And similarly for this one, what we can do is we multiply 6 minus k over 3 by k, and then we minus 3, 0 equals to 0, and we divide by 6 minus k over 3. What's left is this value k. Okay, and to find the stability of the system, what we do is we see if there is a change in the first column here. So what we have is 1, 3, 6 minus k over 3, and k. So for the system to remain stable, there should be no sign change in the first column here. Thus, what we do is we have k must be greater than 0, and also 6 minus k over 3 must be greater than 0 as well. So we rearrange them. What we have is actually k less than 6. And we know that we have these two terms, k greater than 0 and k less than 6, and then we combine together. What we have is actually k must be greater than 0 and k also must be less than 6. This is the range of k for the system to remain stable. What does it mean? Actually, when we see this kind of range, we know that at some point this is the S-plane, and this is the j omega axis, this is the real axis, and we know that from this at some point when we increase the value of k from 0, 1, 2, 3, 4, 5, the system will be stable. But at k equals to 6, the system becomes marginally stable, where we have we don't know the exact location of the poles, but we know that it must be somewhere on the j omega axis. Okay, it must be somewhere. It is not this location, but somewhere in the j omega axis. In this position, the value of zeta is equals to 0, and then we know that at this location the time response for this should be undamped. So what does it mean? When we have undamped system, we have oscillation that neither decay nor increase. Okay, so this is actually what does it mean by k equals to 6 over here. And at this location, actually, when we have a test signal, for example, step, ramp, or parabolic, this is the minimum of steady state error that we have, because when we have more, when we increase the k more, what we have is we have the poles on the right hand side. So when the poles is on the right hand side, the system is no longer stable. All right, and we can show this actually using the MATLAB. So let me show you the MATLAB here. So we have here this is the system GA4, where we have from this example 4, we have this term here, 1 over s plus 1 s plus 2. Okay, and then we can plot the root locus, R locus GA4 here, and what we have is we have this kind of plot. This is the root locus plot. I will cover this in the next topic. What you can do here is actually when you double click on the line here, you will see some parameters shown in the on the plot. So basically, when you move the black dot over here, so at this point of location, we can see when we have k equals to actually when we have at this location the open loop poles, we have a k equals to 0. All right, so meaning that at that position there is no k in the diagram. Okay, so when we introduce k in the system, okay, we introduce the k, the block diagram there, and then we increase the value of k, we can see that the system's on the left hand side. On the left hand side, we increase further until at some point gain increase 2, 3, and at this location here at the j omega axis, the gain becomes 6. Okay, the gain becomes 6. At this position, we can see here the overshoot is 100%. Okay, 100%, meaning that what happened is the overshoot will always neither decay nor increase at this position. Okay, and I can show you as well using the CISO tool. So I run CISO tool for this GA4, and what we have is we have this kind of plot here, and we are not interested in the board editor for a moment, and I close this. I just want to focus on the root locus editor and the step response over here. So when we have C here, this is actually the k value. So when we have k equals to 1, the system is, you see the red plot, red dot over here. This is the system on the left hand side of the S-plane. So when we increase the value to 2, it is still on the left hand side. I increase to 5, it is still on the left hand side, but you can see here the oscillations, the overshoot is greater. It's about 80%, 1 and 1.8, so it's 1.8 minus 1 over 1 multiplied by 100, we have 80%. And when I increase the value of C to 6, you can see here the oscillations is becomes neither decay nor decrease in this case. So the poles it is actually located on the j omega axis. At this position, zeta equals to 0. The response is undamped, and the system we can say is marginally stable. All right. Next, I will show you another example in a different video. So please keep keep reviewing this video until you understand the concept of Routh Table criterion and the locations of a K when the system becomes marginally stable. Until then, see you in the next video. Bye bye.